Welcome to an overview of the Neutron control system. This system manages key components of the Neutron compact neutron source being built near Budapest, Hungary. The Neutron compact neutron source comprises of four major systems: the hydrogen ion source, the 2.5 MeV radio frequency quadrupole, or RFQ, the lithium target station and neutron instrument stations. For this video we'll focus on the control system for the 2.5 MeV RFQ, which was built by Time Company Limited in Japan. The Neutron RFQ is a pulsed accelerator that can support 1.25 millisecond pulses at a rate of 40 Hz for a maximum duty factor of 5%. The RFQ can accelerate a peak beam current of 20 mA with an input RF power of 260 kW at 200 MHz, providing an average beam power of 2.5 kW. The control system for the Neutron RFQ uses the Blinky-Lite control platform. For portability, reliability, and security, all Blinky-Lite user applications are web apps. For security, Blinky-Lite requires an HTTPS connection. Any attempt at using an HTTP connection will be redirected to an HTTPS connection. A user must first obtain a login from the system administrator to access the control system. Blinky-Lite uses role-based access with JSON Web Token (JWT) technology for logging into the system. The user is assigned a role to protect the system from the user making inadvertent settings. For read-only access, the user must have the following roles: reading, ping, read database, renew, app view, and core view. For setting access, the user must have the following roles: reading, setting, ping, read database, write database, renew, and app view. The login JWT has an expiration timer that is set in the user profile by the system administrator. The timer can be extended in the user card found at the bottom of most of the applications. In addition, login JWT expires when the user closes the browser session. Upon entry to the website, the main application index page is displayed. Most of the applications are for troubleshooting. The main application for turnkey operations is the Bridge Control app. This is how the Bridge Control app will look on startup. If the RFQ is off but all water systems, vacuum systems, and the power amplifier is running, there will be a green permit LED in the status card. All alarm LEDs on the right-hand page of the status card should be green. Alarm LEDs have the following color scheme. Magenta means the parameter is below the low limit and is in the alarm state. Blue means the parameter is below the low limit and is in the warning state. Green means the parameter is okay. Yellow means the parameter is above the high limit and is in the warning state. Red means the parameter is above the high limit and is in the alarm state. If any alarm is outside the low or high limit, the machine permit will not be enabled. There will be a discussion later on the steps to be followed if the machine permit is off. The LRF on-off button is the main activator for the machine protection system. If the machine permit has dropped, the LRF will turn off and stay turned off until the user turns it back on. The next step is to turn on the LRF in the control card. With the LRF on, the RF power amplifier is ready to be turned on. In fact, the RF power amplifier can be turned on before turning on the LRF. The power amp is turned on by pressing the button in the control card. The amplifier will take some time to turn on, about 15 seconds. While the amplifier is turning on, the power amp on LED in the status card will remain gray until the power amplifier is ready. The power amp on LED in the status card will turn green when the amplifier is ready. Once the power amp on LED in the status card turns green, the RF power on button on the control card can be pressed. Once the RF power on LED on the status card turns green, traces should appear on the scope plot card. The forward and reverse power traces are shown in brown and gold. The forward power should be close, but not exactly, to the requested power shown in the status and control cards. The forward and reverse power, sampled in the middle of the pulse, are shown in the status card. The reverse power should be less than 10% of the forward power. If the reverse power is large, there could be an issue with the phase lock, which will be discussed later. The cavity voltage vector components, normalized to the power coupler, are shown in the blue shaded traces. These traces are sampled in the middle of the pulse by the LRF and report a cavity phase. This phase is used for the phase lock system, which keeps the cavity in tune. The requested power, repetition rate, and pulse length can be adjusted from the control card. However, there are limits on how much these parameters can be adjusted. The range of these parameters can be seen by clicking the parameter alarm LED on the right-hand side of the app. For example, the alarm range of the repetition rate is shown. If an entry is outside the low-low-high-high alarm range, the machine permit will drop. The app will prohibit making setting changes outside the low-low-high-high alarm range. However, if the alarm range is changed so that the current setting lies outside the new alarm range, the machine permit will drop. The Bridge Control app gives a quick overview to RFQ operations. However, there are hundreds of parameters in the control system that need to be at the correct value for the RFQ to operate appropriately. If any one of these critical parameters goes outside its low-low-high-high alarm range, the permit will drop and the LRF will be inhibited. For example, the machine permit will drop when the pulse repetition rate has been set too low. What system pulled the machine permit can be seen on the machine permit app. For example, it is clear here that the timing system pulled the permit. The specific parameters that are in alarm and the type of alarm can be detailed in the Alarm Scanner app. The alarms are grouped into alarms which are parameters that are outside the low-low-high-high limits and warnings which are parameters outside the low-high limits. Alarms will pull the machine permit, warnings will not. Shown here is an example in which the pulse repetition rate has been set too low. When the machine permit is pulled, the LRF will be inhibited. The LRF will stay inhibited until it is turned back on again, even if the critical parameter goes back inside its low-low-high-high alarm range. This often happens during a vacuum pressure spike. For example, here we see the machine permit being cleared when the pulse repetition rate has been set inside allowed range. The machine permit is clear but the LRF is still off. So now the user does not know why the machine permit was pulled. To find out which parameter caused a machine permit abort, the Blinky-Lite control platform provides a post-mortem application. When the machine permit transitions from good to bad and abort, the control system sends out a broadcast to all the subsystems to save their current state in timestamped archive database. The machine permit app shows a list of all the machine permit aborts. The user can then select one of the machine permit abort events to see what parameters pulled the machine permit. For example, as shown here, in which the machine permit abort was caused by setting the repetition rate too low. Almost all operational issues should be handled with the Bridge Control app. However, for optimum performance, the parameters of individual subsystems will need to be adjusted or viewed. The RFQ accelerator is powered with a 300 kW solid-state amplifier operating at 200 MHz. Basic operation of this amplifier can be done with the Bridge Control app. However, along with basic operation, the alarm, warning, and watchdog status can be monitored with the RF Power Amp app as shown here. The peak RF power sampled at the middle of the pulse is shown in the status card. This readback is based on a headless oscilloscope monitoring the diode-detected output from the front panel of the power amplifier. The headless scope also provides the traces in the scope plot card. The RF power is also reported in the amplifier status card, which is derived from the amplifier manufacturer. Since these are both diode-detected devices, there will be some discrepancy in the readings due to calibration. The descriptions for the alarm and warning codes shown in the amplifier status card can be found in the manufacturer manual. An online version of the codes will be added in the future. If the amplifier trips due to an error such as reflected power, the amplifier error will be reset in the amplifier control card. The power on sequence should be followed just as outlined in the RFQ startup steps described earlier in the Bridge Control app tutorial. The settings of the headless oscilloscope monitor, such as the triggering and record length, can be adjusted in the RF Power Scope control card, but these settings should be rarely, if ever, adjusted. The RFQ vacuum system consists of two turbo pumps mounted directly on the RFQ. The turbo pumps can be isolated from the RFQ via fast gate valves mounted between the turbo pumps and the RFQ body. The exhaust of the turbos is handled by dry scroll backing pumps, one for each turbo pump. The gate valves and the backing pumps can be operated remotely via the RFQ vacuum application. However, the turbo pumps require manual startup and shutdown as detailed in the online vacuum manuals. The vacuum pressure units are in log Pascal, that is 1 × 10⁻⁵ Pascal is equal to -5 log Pascal, and 1 × 10⁻⁷ Pascal is equal to -7 log Pascal. The time plot and archive plot cards show the vacuum pressure evolution and history inside the RFQ, gauges 3 and 4, and in the exhaust lines, gauges 1 and 2. The RFQ vacuum app also displays the backing pumps control cards and the turbo pumps status card. The RFQ has 2 water cooling headers, one upstream of proton acceleration the inlet and one downstream the outlet. Operation of the chilling units is detailed in the online vacuum manuals. The temperature of the water cooling channels is presented in the RFQ temperature app. As with all Blinky-Lite applications, the alarm limits can also be edited by clicking on the appropriate alarm LED on the right-hand side of the card. As stated earlier, a reading outside the low-low-high-high limits will pull the machine permit. In addition to measuring the water cooling temperature, the upstream and downstream water flow for each cooling channel is measured. The flows are measured with ultrasonic clamp-on sensors. The flows of the water cooling channels is presented in the RFQ water flow app. Any alarms in the water flow will also pull the machine permit. The low-level RF, LRF, controls the amplitude and frequency of the RF signal that is fed into the RF power amplifier. The system consists of 3 subsystems: the RF source, the phase detector, and the LRF scope. The function of the RF frequency source is to provide pulses of 200 MHz RF with frequency and amplitude control. In addition, it provides a local oscillator signal to the phase detector module and in return receives a frequency error signal from the phase detector. The RF signal is generated by a direct digital synthesizer, DDS, implemented on a red Pitaya STEMLab 12514, a credit card-sized RF signal acquisition and generation platform. The clock of the STEMLab 12514 is 125 MHz, so a 200 MHz signal for the RFQ cannot be generated directly. Instead, a 12.5 MHz signal is generated by the DDS, and then this signal is multiplied up to 100 MHz with an 8 times phase lock loop. The signal is then frequency doubled to 200 MHz. The phase increment on the DDS is set by a 32-bit word, so the final frequency resolution is less than 0.5 Hz out of 200 MHz. The RF frequency source is the main actuator for the machine permit system. When the machine permit system detects a fault, the tray code resets the direct digital synthesizer, which disables any RF output from the RF frequency source. The purpose of the phase detector is to measure the phase between the cavity drive and the cavity field. The phase difference is sent to the RF frequency source so that the RF frequency source will track the cavity resonance as the cavity temperature changes. The circuit compares the in-phase and out-of-phase components of the RF drive with the cavity field and provides I-channel and Q-channel outputs. The IQ channels are digitized by a STEMLab 12514. Because the signal is pulsed, the phase error is sampled and held in the middle of the pulse and is fed forward to the frequency source. The status card of the LRF application displays the cavity voltage detected by the cavity pickup and normalized to the coupler voltage measured at the center of the RF pulse. The phase signal is the comparison between the RF wave sent to the power amplifier to the RF wave detected at the cavity pickup. The absolute value of the phase signal is arbitrary and, in addition to the location of the cavity resonant frequency, is affected by cable lengths in the system. Relative changes of the phase can be used to determine if the cavity resonant frequency is drifting. Below the status card is the LRF scope plot, which shows the magnitude, in-phase and out-of-phase components of the cavity voltage. The LRF scope plot can be adjusted in the LRF scope control card, but most of these parameters should be rarely adjusted. The RF frequency and amplitude are set by the parameters in the RF source control card. Phase Inc sets the RF frequency without phase feedback. RF amp high sets the amplitude of the RF pulse in units of kilowatts. It is the same parameter as the requested power parameter displayed in the control card of the bridge control app. RF amp low sets the offset value in the RF gate and is used to minimize the leakage voltage in the RF gate. Clear turns off all components in the RF frequency source FPGA. Reset DDS turns off the direct digital synthesizer. It is the parameter used by the machine permit system to stop RF power to the RFQ. It is also the logical inverse of LRF on shown in the control card of the bridge control app. FB filter shift controls the low-pass filter that filters noise coming from the phase detector error signal. A value of 1 is a filter with a corner at 62.5 MHz. A value of 2 is a filter with a corner at 31.2 MHz. A value of 18 is a filter with a corner at 477 Hz. FB gain shift reduces the amplitude of the phase detector error signal. A value of 1 reduces the signal by 2. A value of 2 reduces the signal by 4. A value of 12 reduces the signal by 4096. Due to resistive losses in the cavity will heat up while running at high power. As the cavity heats up, it will very slightly increase in size, and the cavity resonant frequency will then shift downwards by several cavity bandwidths. To maximize the power delivered to the RFQ, the frequency of the RF power must match the resonant frequency of the cavity. To measure the shift in resonant frequency, the phase detector measures the shift in phase between the RF wave sent to the power amplifier to the RF wave detected at the cavity pickup. With a phased locked loop, this changing phase can be used to shift the frequency of the RF source to track the cavity resonant frequency. The parameters in the phase detector control card are used to tune the phase lock feedback loop. Phase target is the phase in which the PLL will lock to. Sample time is the time from the start of the RF pulse in which the phase for the PLL is measured. This parameter will be controlled by the easy setup timer. FB multiplier is the fine gain control of the PLL. Clear turns off all components of the phase detector FPGA. Clear FB turns off the PLL. It is the same parameter as the phase lock on parameter displayed in the control card of the bridge control app. Phase LPF shift controls low-pass filters on the input IQ signals from the phase detector analog electronics. A value of 1 is a filter with a corner at 62.5 MHz. A value of 2 is a filter with a corner at 31.2 MHz. A value of 10 is a filter with a corner at 122 kHz. Load clock delay is the length in 8 nanosecond intervals in the sample and hold of the PLL. FB shift L increases the gain of the phase error signal. A value of 0 has no effect. A value of 1 increases the signal by 2. A value of 2 increases the signal by 4. DAC offset is used to null the signal supplied to the frequency error input of the RF source. To set the correct phase target for the PLL, it is recommended to do a frequency scan of the RFQ at low power. To do a frequency scan, the PLL should be disabled. If the RF frequency is not at the cavity resonance, the reflected power from the RFQ will be large. Now the source frequency is adjusted until the reverse power is minimized. At this point, set the phase target equal to the measured cavity phase at resonance and then turn on the PLL. The Neutron RFQ is a pulse system, so a timing system is required. The Neutron timing system is an 8-channel system based on a 32-bit counter clocked at 125 MHz. The resolution of the timing system is 8 nanoseconds and can have intervals as long as 17 seconds. The Neutron RFQ uses 5 of the 8 channels. Channel 0 is used for the RF source and phase detector. Channel 1 is used for the LRF scope. Channel 2 is used for the RF power amplifier pulse gate. Channel 3 is used for the RF power amplifier sample and hold. Channel 4 is used for the RF power amplifier scope. These channels can be configured with the timing application. To change the pulse length of the RFQ, all 5 channels would need to be adjusted together, which would be time-consuming and error-prone. To make it easier to change the pulse length, a virtual system called the Easy Setup Timer was created. This virtual system will adjust all 5 channels synchronously. All the user needs to adjust is the rep rate, which controls how often the RFQ is pulsed. This is the same parameter as the rep rate parameter in the bridge control app. Easy Setup Timer pulse length sets the length of the RF pulse. This is the same parameter as the pulse length parameter in the bridge control app. The other Easy Setup Timer parameters are the offset, which is how far the RF pulse is offset from the start of the interval, and the PA cushion, which controls how much time on the leading and falling edge of the RF pulse to add to the RF power amplifier gate. In addition to the control system, there are a number of auxiliary systems such as the cooling skids and the turbo pumps that are manually controlled. The Blinky-Lite control platform provides a manuals app where these manuals are readily accessible. These manuals are pointers to other web pages which can be easily edited with other web editors such as Google Docs or GitHub Markdown. That wraps up our overview of the Neutron control system. Thank you for watching.